All right. So next, next on our path of looking at angular motion, rotational motion, is to talk about how it applies to constant acceleration, right? And so we're going to compare the equations for constant angular acceleration with those of linear motion, and you can see that pretty similar in what they are. Anywhere you see linear velocity, you have angular velocity. Anywhere you see linear or tangential acceleration, you see angular acceleration. So everything's pretty close, right? We're rotating. And so the problems will be similar. You just use different information to get there, okay? So let's talk about rolling motion here really fast, and then we'll do a couple of examples. So you got a wheel. It's rolling without slipping. Okay, so that means there's no it's rolling. There's nothing going backwards, right? Our force is staying constant going to the direction it's rolling. At point P, that's touching the ground, is instantly at rest. The center moves with the velocity of v. Okay, the same wheel where C is now at rest, point P is moving with a negative v velocity. So again, looking at from point P, C is going this way. Looking from point C, P is going this way. But the velocity is the same, just positive and negative going different directions, okay? Remember the relationship between linear and angular speed is V equals radius times angular velocity. And that will be helpful when we talk about rolling motion, all right? So let's talk about centrifuge here. A centrifuge rotor is accelerated from 430 seconds from rest at 20,000 RPMs, which is revolutions per minute. What is its average acceleration? And through how many revolutions has the centrifuge rotor turned during its acceleration period, assuming constant angular acceleration? Do it now.
All right, so centrifuge. We know that it's going from 0 to 20,000 revolutions per minute in 30 seconds. So step A is find the acceleration, the angular acceleration. And then part B says how many revolutions has a centrifuge rotor turned during its acceleration period, assuming constant angular acceleration. So first step is we want to find revolutions per minute, and we want to make this into a actual angular velocity. So we know that we get 20,000 revolutions per minute. I know 1 minute is 60 seconds. So that gets me to seconds, and then 1 revolution is 2 pi radians. Okay, so that's where I'm going to get to. So I'll do this math on the calculator, and I get 20,000 times 2 pi divided by 60, and I get, we'll go 2 sig figs, 2100 radians per second. All right, so I'm at radians per second. So now I have a true, can't talk revolutions, or radians per second. So now I have a true angular speed. So now final angular velocity minus initial, the initial 0 over time. So it's just going to be 2100 radians per second divided by time, which is 30 seconds. And that will give you my angular acceleration. So I'll take 2100 divided by 30, and that gives me 70 radians per second squared. And that would be my angular acceleration, which is useful for the next part. So the next part, we want to find number of rotations. So it's going to be this equation, right? So this is going to be our radians of rotation. We take our initial, which is 0, plus 1/2 a times t squared, and that will tell me my distance in radians. So 0.5 times 70 times 30 squared. So that's 31,500 radians. But now we want to get radians to revolutions. And 1 revolution is 2 pi radians. So if I take my answer, look out, from before and divide it by 2 pi, I get about, I want to say 50,000 revolutions. But I get, let me try that again. I got to put it in radians, don't I? My calculator has to be in, it is in radians. There we go. 31,500 divided by 2 pi, 50,000. Revolutions. That's not right. 31,500 divided by 2 pi, 5,000. I knew I was missing a point there. Didn't have my 2 pi in parentheses. 5,000 revolutions, that's better. So that makes 5,000 revolutions during this time frame.
And then we're talking about a bicycle. So a bicycle slows down uniformly from 8.4 meters per second to rest over a distance of 115 meters. Each wheel and tire has an overall diameter of 68 centimeters. We want to determine A, the angular velocity of the wheels at the initial instant, B, the total number of revolutions each wheel rotates before coming to rest, and C, the angular acceleration of the wheel, and then D, the time it took to come to a stop. Lots here, lots of good stuff. Do it now.
All right, so here's our bicycle tire with a radius of, the diameter is 68, so the radius is 34 centimeters. Linear velocity of 8.40 meters per second, final linear velocity of 0, so it comes to a stop over a distance of 115 meters. So part A says the angular velocity of the wheels at the instant it starts going. So we want to find an angular velocity here, right? So here's our equation, right? Linear velocity is angular velocity times radius. To find this, so to find our angular velocity, we take linear velocity divided by radius. So linear velocity, and that's in meters per second, so this has to be converted to meters, so 0.34, and that will give me my answer. And I get an angular velocity of 24.7. Okay, 24.7 radians per second. B then says the total number of revolutions each wheel goes. So that one, not really an equation, but we know that we travel a full distance of 115 meters, so we just got to find what one revolution gets us, right? And our distance is the circumference of a circle, which is 2 pi r. So 2 pi times 0.34 will tell us how many revolutions. So 115 divided by, they get my parentheses right, the calculator, 2 pi divided by 0.34 gives me about 54 revolutions, so 53.8 revolutions. So pretty close to 54 revolutions. C says we want to find the angular acceleration of the wheel. So now we go to this equation because we don't know time, so we're going to use this equation like we would with kinematics. Final angular velocity is going to be 0 because our linear velocity is 0. Our initial we solve for 24.7 squared plus 2 times our A, and then our distance traveled is going to be how many radians. Now to find that distance, right, if we went 53.8 revolutions, you can go a little lower here, 53.8 revolutions, one revolution is 2 pi radians. This comes up quite a bit, doesn't it? So if I take 53.8 times 2 pi, that should get me there, right? 53.8 times 2 pi gives me 338 radians of distance. So this would be 338 radians. Solve for A. So I bring this over, divide by this. Our angular acceleration, 24.7 squared, divided by 2, divided by 338, gives me an angular acceleration of 0. It'll be negative 903 radians per second squared. So there's our angular acceleration. And then D says, what is the time it took to come to a stop? Obviously, I would go to this equation because I know everything except time. Final is 0, initial is 8.4, not 8.4, sorry, 24.7 plus 0.903 as a negative number times time. Bring this over. T wound up being positive, so 24.7 divided by 0.903 gives me 27.4 seconds worth of time. A lot of things can be figured out here. The angular velocity is with taking linear quantities. Big things to remember: 1 revolution, 2 pi r when we're talking about a tire, right? And then also 1 revolution is 2 pi r radians when we want to convert back into radians so that we can use our equations with angular quantities.